Bjorn has served for several years as a Naval Combat Systems Engineering Officer in the Royal Canadian Navy. Operational deployments in HMCS Regina and short posting serving the Canadian fleet. So nowadays you're based in the US?
Correct.
I leave it up to you to tell whether you're Canadian or a US.
I'm still very much Canadian. I have a permanent resident status now in the US. I've been there for 7 years. I certainly, my training in the Navy was more geared towards weapon systems and radars, but I have some passing familiarity with propulsion systems. After I finished my PhD, I joined the US automotive sector, and I've been working in various software mechatronics roles.
Well, I hope your jet lag will bring you in the coming 30 minutes.
Yes.
Doesn't kick in too fast. So the floor is yours, and
Thank
I look forward to this presentation.
Yes. So, as I said, most of my training was naval combat systems rather than marine systems, and so this invention came about not from my naval engineering experience, but from my automotive experience. I was working at a mechatronics company in Detroit, and they make power-operated tailgates for vehicles, which are driven by a threaded spindle. And at the same time, as I had a test bench beside me for this power-operated tailgate, I was considering how one might vary the pitch of a cooling fan in an economic fashion that might be employed on an engine cooling fan. And so the inventive moment was to realize that the two could be merged together. So I filed for patent in the US. I missed the international filing dates. So right now my only control over the invention is in the US. My focus today is to discuss the propeller, but obviously fan, axial or centrifugal, and is not much different than a propeller. And also turbo machinery is certain, operated under varying speed could benefit from controllable pitch technology. But the invention has broader applications. I called it an axial pitch modulating mechanism for rotating shafts. So the invention could be used for clutches as well as swash plates. You can imagine the clutch on the Canadian patrol frigate. I think there's 17 asbestos fiber pads that get pushed together by force on the stator system. So there's friction between the stator system and the rotor system, and this invention could eliminate that mechanical coupling between the two. And the swash plate, obviously, with the pump and the pump rotating around, to adjust the swash plate, the adjustment is done from the stator system. So once again, you have a rotating mechanism in friction with the stator system. So this, again, could eliminate that friction. Turbo machinery. So the invention has actually 3 points of interest for marine propulsion systems. I do believe strongly that it could be used on turbo machinery. There are a few attempts I've seen in the literature. How much they've achieved commercial success, I can't say. But one practitioner suggested that it could potentially offer a 10 to 14% savings for turbo machinery on an aircraft in that case. So turbo machinery, clutches, and then the propellers all could benefit from this technology. So the idea is simple, just as with a threaded nut and bolt, a threaded shaft, a shaft with a thread on it could be combined with a nut, or I call it an axial modulator, which has a thread inside the cylinder, and they could be threadedly mated together. The only other addition really is I call it a pitch modulator, which is coupled together so that they're coupled together in axial motion, but they're free to rotate. So mating them together threadedly. Oh. plastic is almost at its end. I may have offended the Transport Safety Authority when I went through the customs. I think they might have been concerned with what was on board. So this pitch modulator, I put a rack, and on the bottom of the fan blade or the propeller blade, I put a pinion. So it's basically a rack and pinion after this this mechanism is concerned. And so with the two gear profiles interacting with one another, well, I can't quite do it, but you can see that the rotation of the axial modulator causes axial motion, and the axial modulator, the gear teeth, the gear profiles will interact with one another, causing rotation. So it's obviously the mechanical advantage in the thread makes it easy to spin, but axial movement is difficult. So there are two primary means of achieving the actuation. The really strongest advantage is electromechanically, which eliminates all interaction between the stator system and rotor system. And really, it amounts to you would have one motor or propulsor driving the shaft, and then you would have another motor, a reluctance motor, that would spin this. If you were to make this out of ferromagnetic material, obviously the reluctance motor would work on that. If it were made out of a polarized magnetic material, the rotation of the shaft would cause a regenerative issue, and of course that wouldn't be desirable. So the simple reluctance motors are now widely used in high torque applications in automotive. So I think it's quite suitable. However, I imagine you can picture better than I can that some ships, the forces involved would be quite large with the friction in the thread. So a means of providing some sort of mechanical advantage would be ideal. So rather than drive this axial modulator with electromagnet, to do as I've done here and make a gear profile and then drive this profile with a pinion shaft. And so the control for that is simple, but it's a little bit unorthodox. The tangential velocities, the steady state case would be achieved by having the pinion shaft driven such that its tangential velocity with the axial modulator's velocity, tangential velocity being equal. Of course, then you can imagine that the gear profile wouldn't be actuated. And then when one wants to control the motion forward or aft to induce a slight speed difference on the pinion shaft, which would in turn create a torque, which would cause an imbalance force and cause the gear profile to spin. So there are two ways of doing it, I guess all depending on the application. And as an interesting aside, I'm speaking right now to a flying taxi manufacturer, or would-be flying taxi manufacturer for use in their applications. But the mechanism is simple enough that it can be done in a very small scale. So I'm presently working on a prototype for a drone. You can see here the prototype sitting on my desk, and the keyboard and computer screen gives some sort of scale that yes, this can be achieved on very, very small scale. So, typical outboard motors from a sportsman's vessel could benefit from this technology. So in my paper, I've essentially reduced the analysis to a comparison between a hydraulic cylinder and an electro-mechanical cylinder. The mainstay in controllable pitch right now is obviously hydraulics. And essentially there's a piston inside the rotating shaft, whose axial motion causes the pitch ultimately to be varied. And so that is basically how I've reduced this to something manageable for me to do without large university resources to create actual prototypes to do the comparison itself. So I've done a reasoning by analogy, and the comparison is largely reduced to a comparison between hydraulic actuation and electromechanical actuation. So in the literature I found various studies to try and substantiate my claims. The Canadian Coast Guard has recently done a study where they found their electrical drive winch efficiencies were around 70 to 85%, and ultimately the hydraulic efficiencies dropping significantly as less electronic components are involved, from 45 to 70% and 35 to 60% with hydraulic systems. So I found a very nice paper by Electro-Mechanical, which actually does a comparison between hydraulics and electrics. However, they have a commercial interest, obviously, in it, so it's hard to use their figures for efficiency as definitive. But their claim is that hydraulic efficiency versus electrical efficiency is half of what each is. And that is consistent with what Canadian Coast Guard found with their applications. So the one thing that a hydraulic controllable pitch propeller has beyond the simple backward and forward actuation is the need to force the hydraulic fluid from the stator system onto the rotor system backwards and forwards. So obviously there's mechanical coupling again between the stator system and rotor system. I'm sure from what I've seen in the literature it's quite clever. However, the coupling is there. And the oil distribution box which achieves this coupling is, it does the job, but it's incredibly inefficient. There's a very nice master thesis by Dullins who builds a nonlinear state space model of a hydraulic controllable pitch propeller. And he found that the internal leakages had an enormous impact on the system's dynamics. And the figures in his study suggested again that, well, in addition to the halving of efficiency between electric and hydraulic actuators, there's an additional halving due to this oil distribution box. So obviously, such systems are very complex. There's thermal effects to take into consideration on large ships. The lengths of the shafts add other interesting dynamics. And the problem is really quite sophisticated, and it led to a very nice master's thesis, but there's a simpler way of achieving the actuation. So on a maintenance perspective, there are some nice studies available in the literature on the maintenance involved in a hydraulic controllable pitch propeller. And over lengthy studies, mean time between failure found to be around 165,000 hours, and 26% of those failures due to hydraulics. Difficult, mean time between failures is a less significant figure these days. Weibull analysis would provide a more accurate comparison, but these were the figures I had available. Then in aeronautic applications, this was applications of electric linear actuators, not for controllable pitch, but it was found that mean time between failure was around 600,000 hours. So when one chooses the type of thread, there are a number of choices. There's a standard Acme thread, which I have here. The advantage of that is that it locks with friction. So motion, axial motion, is quite difficult to achieve. In applications where maneuverability is quite high, perhaps a tugboat, the actuation might be constantly required, and that friction, as an advantage in applications where locking is good, would actually make the system quite inefficient. So there are other alternatives like ball screws and cylinder screws, which have very high efficiencies, 95% efficiencies, versus the Acme type threads, which have 30 to 50% efficiencies when the locking mechanism, when the ability to lock isn't as desirable. But from a maintenance perspective, these types of threads have a very high reliability. Roller screws and ball screws having a factor of 25 to 30%, so roller screws being preferred, and they're also capable of achieving a much significant more load rating for a similar size, around 3 to 4. So the only other main component of this invention is the reluctance motor, and I found in the literature that around 500,000 hours mean time between failure was achievable. And again, that's for a standard reluctance motor, which has bearings. In this case, the shaft is already supported, so the reluctance motor for the axial modulator would not need bearings. So the performance of the reliability is almost two to three times that of the hydraulic systems. And this again, just finding other strong points of comparison, was consistent with the Canadian Coast Guard's experience in that hydraulic systems have a substantial maintenance requirement over comparable electric systems. Weight. So when you consider a hydraulic system, obviously there's oil reservoirs, the pump, hose lines, the oil distribution box, gauges, temperature control mechanisms, all of which add complexity, but they also add significant weight. And it's perhaps less critical on a ship, but on an aircraft, there have been substantial savings by switching to electric systems. As much as 10% of 10% weight savings has been achieved. Again, not for controllable pitch applications, but other transitions from from hydraulic to electric achieve that type of savings. So the system is quite simple. I've suggested that it produces a new Pareto optimal boundary of variables in terms of efficiency, 2 to 3 times, perhaps more. Maintenance requirements, again, 2 to 3 times improvement in reliability. Weight reduction of 10%, and other soft factors like environment and reduction of hydraulic leaks, space, thermal management. So in all respects, I think this is a significant simplification over the state-of-the-art, which has wide applications. I do have numerous prototype videos on my YouTube channel. If you type Jordan McBain and controllable pitch into Google, it will bring those videos up immediately, so you can have a look at the system in actual operation. Yeah. So short but sweet, consistent, I hope, with the simplicity of the device.
Thanks. Thank you for this very interesting talk. Any questions?
We did look at a rack and pinion type arrangement years ago, and it
Yep.
got up to about a 1,500 millimeter propeller. The spindle torque and the loads and the backlash in the gear made it, anything bigger than that made it pretty much impossible to make it work. friction, there's no roller bearing that actually rotates the blade.
Mhm.
And so the load isn't spinning at full speed. The loads actually pitch the blade quite high.
Okay.
So, and then pushing on it, on your design, you're showing the actuation very close to the hub.
Yep.
Generally, the actuation is at the other end
Yes.
of a relatively long shaft.
Yes.
3 or 4 diameter
Mhm.
blade.
So I think my suggestion would be that the mechanism would be in the hub itself. And where the rack and pinion is concerned, this is how I chose to realize it in this case. So far, once you get the axial motion from the mechanism, how you achieve that, you could use a standard means of, I think it's just a block with a profile on it that interferes with the base. Yeah, can, yeah. So you could use that as well, rather than a rack and pinion.
Regarding pitching, any possibilities to lock the pitch position?
Yes, so inquiries I typically get are, do you consistently need to apply energy in order to maintain the state of the mechanism? And so it's the thread that really makes this a robust means of control, because once you've rotated it to the position you want, axial force makes it very difficult to. The mechanical advantage in the thread essentially provides a locking mechanism for it, and the forces involved, may certainly cause motion. And on its face, the hydraulic system, the ability to control the proportional control valves or whatever valves in order to lock things into place, would seem to be a better solution. But again, the leakages in the oil distribution box effectively make the locking mechanism not as significant as one would think. So I would suggest that the locking mechanism in the Acme thread is just as significant, or just as good or better than the locking mechanism in the hydraulic system.
Yeah, well, first congratulate you for being the only presenter to come up with a physical model today, so well done, and even more congratulations getting it through the immigration customs and security and all the rest of it. My question's really a non-technical question. You haven't mentioned anything about costs.
Cost.
Have you looked at costs, whether it's UPC type costs or even better through life costs, to see whether that would help you sell this idea?
My analysis as to cost is just reduced to the simplicity of the mechanism. In terms of comparing it to hydraulics, the number of components, the sophistication of the mechanism, I expect a drastic reduction in costs. And so this was one of the things that was important for the automotive sector with the engine cooling fan. A hydraulically driven cooling fan to control pitch would just make the mechanism economically infeasible. So this mechanism is simple and easy to implement. So I think bringing it in range of affordability for cooling fans.
Well, while reading your paper as preparation, I noticed indeed your maintenance topic, your mean time between failure is related to the early 1970s.
Yes.
It's the time when I was also built with the
Yeah.
mean time between failure. But do you think these days, because I know at least we have developed quite some new hubs, etc. over the years.
Yeah.
Do you think your number is still valid, or are you now a little bit cherry picking?
No, that's a good question. I think the improvements in those numbers would be small. In the end, it's since the 1930s, hydraulics have been used in aeronautical applications. Obviously, I think probably ships earlier than that, just a decade or so. And so it's always been a hydraulic mechanism moving backwards and forwards. And hydraulics are just riddled with difficult maintenance issues. And obviously that assumes a perfect scenario where one is doing proper preventive maintenance and monitoring, whereas most operators, I don't know if they achieve that in there.
No, I think the trend towards say getting rid of hydraulics and going to electronics is it's a very good step. I mean, one way or the other
Yeah,
to
yeah.
make it a success. Do we have any other questions? Well, we are happy with it, and thank you for your.
Yes, thank you.
Well, then, thank you.